So guys, I have a request for you. So after you have watched the entire video, like can you comment down below whether you have understood the video or not? You don't need to like or subscribe the video. You just need to comment down below whether you have understood the video or not. And this will help me in making better videos for you in the future. So in this video, we are going to be discussing today's POD, today's lead code problem of the day. Number of steps to reduce a number in binary representation to 1. So basically they will give us a binary representation of some value. Binary representation we have to, okay, and they have provided us with two steps. So either we can divide this binary representation by 2, we can divide by 2, or we can add 1 to it. So suppose the binary representation that they have given us is 1 0 1 1. Okay, in the question they have taken the lowest set bit as the rightmost bit. So we have to count from start from the this rightmost bit. So we have to start to 2 raised to 0 from here, 2 raised to 1 here, 2 raised to 2 here, 2 raised to 3 here. But I am more familiar with writing the lowest set bit on the left hand side. So I'm gonna reverse this. That's purely for my convenience. You can do anything according to your convenience. I am reversing this string because uh, for me it's better, like for me it's more convenient to write in the reverse order. So now I have reversed this particular string. So this will right now be in the format 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3. So when we convert this into the decimal representation, it will be 1 into 2 raised to 0 plus 1 into 2 raised to 1 plus 0 into 2 raised to 2 plus 1 into 2 raised to 3. That will be equal to 1 plus 2 plus 0 plus 8. It will be equal to 11. So suppose they have given us a value 11. So in each operation we can divide by 2, or we can divide 11 by 2, or we can add 1 to 11. And we can only divide by 2 if it's an even number, and we can only add 1 if it's an odd number. So in the so and our objective is to convert this particular 11 into 1. We have to use some number of moves and convert this 11 into 1. So the number of the moves required to convert 11 into 1 are, we have to first add 1 to 11, because 11 is an odd number. We will add 1 to 11. So this is move number 1. Then it will become 12. Since it's a even number, we have to divide by 2. It will become 6. This is move number 2. Since 6 is an even number, we have to divide by 2. It will become 3. This is move number 3. Since 3 is an odd number, we will add 1 to 3. Then it will become 4. This is move number 4. Since 4 is a even number, we will divide by 2. It will become 2. Move number 5. Since 2 is an even number, we will again divide by 2. It will become 1. This is move number 6. So total we took 6 moves to convert 11 to 1 according to the operations that they have given us. Okay, actually this is very straightforward question. If we are able to convert this binary representation into its corresponding decimal value. But the problem with the question is that this binary representation can be, the size of this binary representation can be up till 500. So what is the integer limit? The integer limit is like 2 raised to 32, right? So since they have given us the value will go up till 2 raised to 500, that will be very huge, very huge, and it won't be contained within our computer memory limit. So this is not feasible to convert it into decimal first, and then apply these operations sequentially, it won't be like it won't suffice. So we have to think of some other approach. So the approach that I thought of is I will show you two approaches. The first approach is like the brute force kind of approach, but it will work. It will pass the cases. It pass the code. Then the second approach is a more optimized approach. Okay, like I will show you the first approach first. So it will be easier for you to think in terms of that. So I will give you a test case. This is a test case. Okay, this is also a test case that they have used in the problem. The test case is 1011. The test case in the problem that they have given us, they have given us 1101, but I have reversed it for my convenience. I have reversed the values. So what will be the decimal value for this? Decimal value for this is I'm just writing the decimal value for explaining purposes, but we are not going to compute the decimal value in the solution that we have formulated. The decimal value for this will be, this is 1, this is 4, this is 8. So it will be equal to 13. Okay, so now let us see, like we have two operations, right? If it's even, we will divide by 2. If it's odd, we will add 1. Okay, now when is this binary representation odd? This binary representation is odd when the first bit is 1, right? When the first bit is 1, when the first bit is 1, we will add a 2 raised to 0 to every number. 2 raised to 0 is 1, so it will become odd automatically. So this binary representation is odd when the first bit is 1. So when the first bit is 1, we know that we have to apply this add 1 operation. What happens when we perform this add 1 operation? When we perform this add 1 operation, I will show you with an example. So if I perform this add 1 operation to this one, okay, like I will write the decimal representation for each bit again. So decimal representation for each bit is 1. Since this is not a set bit, I will write the 0. This is 4. This is 8. So when I apply the plus 1 operation to this, we have to add plus 1 to the lowest bit. We have to add plus 1 to the lowest bit. So when we add plus 1 to the lowest bit, it will become 2, right? It will become 2. So this bit will become 0, and since it became 2, this will become 2, and it will become set, and this will become non-set. So after the addition of one operation, the binary representation that we will obtain will be 0, 1, 1, and the corresponding decimal values for each bit will be 0, 2, 4, 8. Because like we added the original bit value was 0, 1, 0, 1, 1, and it was 1, 0, 4, 8. Since we add 1 to it, so we have to add 1 to something, right? We have to add plus 1. We have to add plus 1 to something. It's like we can add plus 1 to any of the values over here, but it's better that we add it to the first bit, because like if we add plus 1 to the first bit, it will become 2. 2 is a power of 2, so it will be more convenient for us. Like if we add this plus 1 to any of the other bits, like suppose we add it to 4, it will become 5. It's not a power of 2. It will become very inconvenient for us. So that's why we are adding it to the first bit. When we add it to first bit, it will become 2, right? So now it's no longer 2 raised to 0. It's now 2 raised to 1. It's no longer 2 raised to 0. It's now 2 raised to 1. 2 raised to 1. So we have to move it to over here, and the 2 raised to 0 value that we had here disappears. So that gets converted to this. Okay. This is what happens when we add plus 1. Now what happens when we divide by 2? When we divide by 2, we have to divide the entire binary representation by 2. So this becomes 4. This becomes 4. This becomes 2. This becomes 1. So there is a shift. 1, 2, 4, 0 1 1 1 0. So this value gets converted to this value. So what's basically happening is that every set bit is getting, shifted to the right by getting shifted. Okay, right shift, we can say right shift. Every set bit is getting shifted to the right by 1 bit. That's what happens when we divide by 2. Okay, suppose like if the value that they have given us is 0 1 0 1 1. So if we divide this by 2, every set bit will get shifted to the right by 1. No, actually it gets shifted to the left, right? So that's my fault. Okay, I got confused between left and right. It's getting shifted to left, right? Sorry, my mistake. Left shift. It's getting shifted to the left by 1. So if you apply a division by 2 operation on this, every set bit will get shifted to the left by 1. So if you divide by 2, the corresponding, the value for this binary representation would become 1 0 1 0 0. 1 0 1 1 0. So every left every set bit is shifted to the left by 1, and the last bit becomes 0, because there is nothing to shift to this bit, so it becomes 0 automatically. We can consider it as 0. And I will give you another case for another okay, this is what happens when we divide by 2, and when we add by 2, this is what happens. Like the bits get shifted to right. Okay, in division by 2, all the bits irrespective of their position gets shifted to the left by 2. But when we add, it's not necessary that all the bits irrespective of their positions will get shifted to the right. So suppose if you perform addition +1 operation on this, only this bit will get shifted to the right. This will become 0, this will become 1. But suppose for another then this value, this binary representation will become 0 1 1 1, right? But if you perform one more addition operation on this, so no, not on this one, I will give you another string. Okay, suppose if you perform +1 operation on this string, what will happen? What are the corresponding decimal representations? This is 1, this is 2, this is 4, this is 0, because it's not a set bit. So if we perform +1 operations on this, we will add this +1 to the first bit. So we will add it to 1. It will become 2, right? It will become 2. There's already a 2 here, there's already a 4 here, there is 0. Since there are two 2's, it's better to combine them. So we combine these two 2's. Then it becomes a 4. There is already a 4 here. Since there are already two 4's here, it's better to combine them. We combine these 2 as well, these 4's as well. Then it becomes 8. So the binary representation that was this, when we added a +1 to this, it became 0 0 0 1, because this is 0, this is 0, this is 0, this is 8, because it's a set bit. So we added 1 to this 1, it became 2. That 2 combined with this already existing 2 to become 4. That 4 combined with the already existing 4 to become 8. So it's like a domino effect. So these bits will get shifted to the right as long as there is a continuous sequence of 1. So suppose like there is a gap in between. So suppose there is a gap in between. I will show you. Okay, 1 1 1 0 0 1 1 1 1. Okay, suppose it's like this. There is a gap in between. it should be at least 1 0. So if there is a gap in between, this domino effect will stop here. So we will add a 1 2 here, we will add a 1 to this first bit, it will combine with the second bit, this will combine with the third bit, and it will form and it will become this bit. So the value after we add a +1 to this will become 0 0 0 1 0 1 1 1 1. So it goes on like a domino effect till there is a 0th bit to stop the domino effect. But this is not what happens in in the other case, in the division by 2 operation. The division by 2 operation, every bit irrespective of their position get left shifted by one position, one bit. Okay, this is the main logic behind this. I will show you that the output for the test case. So this is the test case that they provided us, 1 0 1 1. This is the test case that they provided us. So initially it's an odd value, since the first bit is set. So what we will do is we will add 1 to it. We will add 1 to it. When we add 1 to it, this will become 0 1 1 1. Then now it is a even number, since the first bit is not set. So we will divide by 2. So when we divide by 2, it will become 1 1 1 0, since all the bits get shifted to left by 1 bit. Now it's an odd number because the first bit is set. So we will add a 1 to it. When we add a 1 to it, like when we add a 1 to this one, this will get combined with this one, this will get combined with this one, and finally it will stop at this 0. So this will be the answer after adding a 1 to this number. It will go on like a domino effect. And now it's a even number because the first bit is not set. So we will divide by 2. When we divide by 2, it will become 0 0 1 0. All the set bits will be shift to left by 1 position. Then we will divide again by 2. This will be the output. Then we will divide again by 2. This will be the output. Okay, now we can stop, because what is this value? This value is 1, right? What was our goal? Our goal was to reduce the number that the binary representation that they have given us to 1. So we have got the output. And how many operations did we take? We took 1 2 3 4 5 6 operations. So the number of operations required to convert this value to 1 is 6. So that's basically the approach. Actually, you can code the solution using this approach as well. You can directly code this, you have to check the first bit continuously. If the first bit is set, you can do this domino effect operation. If the first bit is not set, we can shift to the left by 1. I will show you the code as well for this this approach. Actually, there is an optimized approach as well for this one. It's a more complicated solution. It's like it takes more time to understand. I will make another video for that, for that approach as well. It will be much easier if we understand this approach. We understood this approach, right? We understood how the bits are changing when we add a +1 to it, and how the bits are changing when we divide by 2. So I will show you the code for this approach now. So guys, this is the approach for the solution that we discussed just now. So in the I have created a separate divide by 2 function, for understanding purposes. In the divide by 2 function, we are shifting each bit of the binary representation. String S is the binary representation that they have given us. I am shifting each bit of the binary representation by 1 bit to the left side. And as I've told earlier, okay, and now we will move on to the main function execution.
as I've told you earlier, like it is more easier for me to uh, process the string, understand the string, uh, you know in the when the lowest set bit is on the left hand side. So I have reversed the string initially. And why did I add a plus another bit to this string? So why did I add this bit to this string is that, so if we check, like if suppose they have given a string like this to us. Okay, what is the value of this? 1 plus 2 plus 4, 7 plus 8. That's 15, right? 50. So suppose they have given us a string like this. Now what is the first operation that we have to do? The first operation that we have to do is add 1 to this. If we add 1 to this, it will go like a domino effect, and it will be like, the resulting string will be like this. So the size of the string has increased by one than the string that they have originally given us. So to handle this condition, I have added an extra bit over here. Uh, in the worst case, only one more bit will get added to the original string that they have given us. So that's why I only added one extra zero bit to the string. Now in the this is the answer variable. Inside this answer variable, I will store the number of operations that we have to perform to convert the string that they have given us to one. And okay, so if the first bit is not set, I will divide by 2. If the first bit is not set, we know that the given binary string is an even number, so we divide by 2. And else, if the first bit is set, what we will do is that we will count the number of set bits inside the binary representation. We do this because, like, uh, so suppose, like, if the binary representation is like this, we have to keep on performing the operations. But if the binary representation is this, we have to stop the operation, right? Because we achieved the value that we wanted. So when do we stop the operations? When the number of set bits inside the binary representation is 1. But if the number of set bits in the binary representation is greater than 1, we continue doing the operation. So I count the number of set bits in the binary representation. If it's equal to 1, we will stop the operation. If it's greater than 1, we have to perform the domino effect operation that I told you earlier. So what I do is that I will first set the first bit to 0. The first bit was 1. I will set that to 0. And okay, actually this last variable is, you can imagine this is a carry variable. So we took the first bit and stored it in the carry variable, and we will start the iteration. While the carry bit is 1, we will check whether the current character that we are on is 1 or not. If the current character that we are on is 1 and the carry bit is 1, we have to double it, right? It becomes doubled. So the previous bit, so we took the previous bit and we are adding that bit to the current bit, so it will become double. So when it becomes double, it will get added to the next bit. So it will go on as a domino effect, right? So we have to set the current bit to 0, and we have to set the carry bit to 1, as like same, equal to 1 as well. But if the current bit is not 0, if the current bit is not 1, the current bit is not 1, the domino effect will be stopped over there. So we will convert the 0 bit to 1, and we will set the carry as 0, because the domino effect is going to stop over there. I told you, right? When a 0 appears, the domino effect will be stopped over there. So that's what happening over here. And we will print the and will store the number of operations required. and I'm printing ants minus one. Okay, like I printed ants minus one because like I placed ants over here. I should have placed ants over in the end of the while loop. Then you can directly print return ants. Like it depends on how your implementation is gonna be. So if you like, I since I place ants plus plus at the beginning of the while loop, I'm counting the initial string as well, and the file. I think I'm counting the final string as well. That's why that's happening over there. So if you place it at the end of the while loop, it won't happen. You can directly return ants. Okay, this is my code implementation. Hope you have understood the solution.